Now, on today's lecture, we will be talking about MATLAB and how we will use MATLAB. So let me start with that. So most of the time, if you use MATLAB, you will see this graphical user interface. And for those who don't know MATLAB, we have this program here. You can download it using the educational Roam. So you can see that we have a command window, a current folder, workspace, and command history. They help you out in using MATLAB. And then we also have this new script here. If you click on that, you will create a new script. But most of the time in the laboratory sessions, I will not use this MATLAB graphical user interface. I will rather use the Visual Studio Code extension here. So if you're new to MATLAB, I highly recommend you to use this MATLAB interface. But if you're an advanced user and want to have, as I want to have, a dark interface, then you can also use Visual Studio Code. So there are some extensions that help you out in using Visual Studio Code for MATLAB. As you can see, we have this MATLAB support here. If you wish, I can share you the details, the extensions that I'm using. But let me just remind you that you need a specific Python version, and a minimum requirement is also there for MATLAB in order to get things working. So now,
may I ask something?
Of course.
Can you please create a folder on something like requirements.txt about MATLAB extension on Visual Studio?
Well, basically, this is the core one. So I might try to link them, but it is easier if you have Visual Studio Code. You can just search for MATLAB and then these pop up. And the most important one is this MATLAB Interactive Terminal. So I might give you that, but this is the most important extension. But I'll add a TXT file. So yeah, once you have that, it is pretty easy to use, and I like to use it a lot. So we can open up a MATLAB terminal. Hopefully, yeah. There we go. There's one downside in using Visual Studio Code for such a programming language that is not shipped default. And that is you have to execute the commands twice here. There's some bug or something going on there. I don't know. But if you see me executing it twice, then it's because of Visual Studio Code. So I have also notes for the laboratory for each week. So I will be uploading them. And for the English users, it will be English. For the Turkish one, it's Turkish. And it will be a recap of the session. But sometimes it may differ from the code that I'm writing during the laboratory session, because of the fact that I'm not copying and pasting it. I'm just writing it from scratch. So therefore, there might be slightly differences, but the main point will be the same. So yeah. Let me ask you, what is your MATLAB knowledge? So who says I have never used MATLAB and I'm fairly new to it? So is there anyone who doesn't have MATLAB knowledge? Okay, seems like at least you've heard it. Who says that I can work my way around, I can code, and I use Google a lot and I get things done? So kind of the medium knowledge.
Me.
So the other ones are experts, I guess. No? Orta seviyede biliyorum diyen kaç kişi var? Bir el kaldırabilir mi? Tamam. Umuyorum ki onun da bir desteği olmuştur. Çok iyi biliyorum diyen var mı? Pek çıkmadı. Tamam. Okay, it's just so that I know my audience. Therefore, I go into that detail. So, yeah. let's talk about basic MATLAB knowledge. For control system design laboratory, we will be using three basic stuff in MATLAB. One is, of course, basic MATLAB knowledge. You have to know your way around in MATLAB. You have to know how to debug code and etc. And then there's this control system toolbox, which you might have heard of it. You can easily, for example, you can plot the step response using the step command, etc., etc. So it's basically a analysis tool, control system design toolbox, control system toolbox rather. And then there's also a symbolic toolbox, which we will use a lot in this laboratory sessions. So I will be talking about these three basic requirements here. So let's start with MATLAB, but since most of the time you can find out everything about MATLAB, I will be trying to focus on some useful stuff, hopefully. Yeah. Now, if you know C, a low-level programming language C, then you can use MATLAB fairly easily because it's an easier version of C, basically. And a lot of syntax comes from that. Or if you might know Python, then it's also very, very similar to Python. For example, in low-level programming languages, the code that we write is more of a code that the machine could understand. But in high-level programming languages like MATLAB or Python, it aims to the user, actually. It aims us. So we should understand it better than the machine. Therefore, for example, if we define some variables, let's say we have a variable, we give it a name, but we don't need to specify any type. We can just give the name. But if you define a variable, you have to give it the initial value, even if it's empty. So therefore, what MATLAB does behind the scenes is that it tries to come up with a type suitable for your initial value. So for example, if I give it a 2, in C, we would just define int C and then C equals 2, or we can also combine it like this. So, but in MATLAB, that's not the case. In MATLAB, you just give it a name, give it a value. So what do you expect is the data type of A? Because we have certain data types that we're aware of. One of them is int, which stands for integer. And then we have, if you remember, we have float, which is a floating point number. Then there is a double precision float, which is called double. And then we have a bool. What else do we have? We have char, and you might have heard about string if you use C++ or so. So what is the data type of A? What do you expect as data type? I give it a 2, so it should be basically an integer. But that's not the case in MATLAB. And therefore, let me demonstrate to you that. We have some predefined functions which help us out. One of them is class. So if you have any variable and you don't know what the type is, you can use the class function, pass it to your variable, and then you will see what the data type is. For example, if I pass in a 2, I get a response which says double. So even though I'm defining a variable and it has the value 2, it is a double. It's not an integer. So do you see the problem here or the advantage here? Because it's a trade-off. It might be advantage, or it might also be a downfall. Do you see any issues with this?
Or consume more memory, I think.
Yeah, that's one of them. We need more memory for double. If I'm not wrong, it should be 4 bytes for an integer and maybe 6 bytes or 8 bytes for double. I don't know. So that's one thing. We have too much memory. If I have an array of integers, then this difference will become bigger and bigger. This will increase. But what is the advantage here?
Maybe not the kind of type components.
Well, the advantage here is that you don't define any data type. That's an advantage. It is by default a double. But you should also understand that MATLAB is not a production programming language or a production environment. So we don't care about memory. We don't care about performance at this point. The only thing that we care about is to prototype easily, to get it done. So that's more of the aim of MATLAB. If you're trying to minimize the memory usage, you can also do that in MATLAB. But you should maybe use a low-level programming language for increased performance, increased memory usage, etc. So here in MATLAB, we don't really care about the performance or memory. But the memory might be used and overused a little bit. So that might be the case. But if you define a variable in MATLAB, it's automatically double if it's numerical type. So that's it. Now, is there a way of defining other data types? Of course there is. Before I get into that, I can also show you that we could, for example, check if a certain variable is a certain class. For example, I can say, is it a or is a double? So if I pass in an a, what I can see is I can see if it's a double or not. Of course, I didn't run the script. So let me run the script. So by pressing up and down arrow keys, you can toggle the previous commands here. So you can check if the variable that you've provided is double. Now you can see that instead of having true or false, we have something called logical. So as you might guess, it is about bool. So in MATLAB, we don't call bool or Boolean values. We call them logical values. So it's a logical 1 or logical 0. If you are a computer science student or electrical engineering, if you're studying that, you might already know what logical means. So yeah, in this case, we can see that in float double is covered by double by default. We have logical for bool, and we have also char here. And to define a character here, we need these quotes, single quotes here. And let's say, for example, X. And then we will also talk about string. So I can define any character here, but defining a single character does not help us that much. What we might do is we might extend this to a text, for example. How can I define a text in MATLAB? Now, in C, what we have to do is we have to define a character and then give it some default value, for example, 255. We have some pre-allocation here. And then what we do is we give it, for example, something like this, etc. So in MATLAB, we don't really have to do that. We can define a character vector here in single quotes. So, and let me also show you the string here, how we can define a string. The string is basically the same, but you use double quotes. So do you know what the difference between single quotes and double quotes are? Because you have single quotes, but you can also use double quotes. So which one should I use? Are there any differences? Why is there double quotes, for example? Now, in the C perspective, you might know that there's something called an std string, and it's kind of a new version of a string. But the old school way is to define character arrays. So maybe that's also in MATLAB here. We'll see. We'll see what the difference is. Now, for example, sometimes we want to debug some code, and we might want to do something like this. Let me give you an example. So I want to print out in the console that, for example, A is this value. So I want to display this here. Usually you would use printf and then provide something like this here. Since it's a double or float, I can just do this. So basically, this is what I want to do. I can do this by using fprintf in MATLAB, by the way. There we go. We can printf basically, but we use f in front of it. This is, by the way, very useful if you want to create a TXT file and you want to export some data. All you have to do is you have to write this piece of code here. You should open a file, let's say debug.txt. You should also provide a little flag here if you want to write, if you want to read the file. So we say write. And then you should also close the file here. Now, the only difference is that you should give FID here for fprintf. If you're familiar with programming, you might also know that this terminal here shows you basically the standard stream or the IO stream here. So that's basically the same as creating a file and then writing to a file, because it's a string stream, basically. So fprintf works both ways. You can use the standard IO, which is the terminal. You can print to the console, or you can print to a file. So you can use the same syntax here. And let me show you. There we go. We have created a file which has the exact same output here. The only difference being providing a first argument FID, and that's it. So basically, I want to do this, but I don't want to use fprintf for some reason. Then you can use disp, which is the short for display, and you can provide it before without even converting anything. So you can just say disp A, and it will determine the data type, convert it, and print it out. But what if I want to combine a string and, for example, A? What do you expect for this? Should it work, or what could be the issue here? So any ideas?
I think A will be converted to a char, and it will be something like A column, not two.
Not true.
Character.
So yeah, adding a, for example, double or integer to a character vector, a character, results in the following. You might not have expected it, but this is the result. So if you think about C again, that will be a lot of what will happen today. We will think about C all the time. Now, you might know that a character is just one byte of value. And you can store from 0 to 25 anything on that byte. And that's basically it. So we don't have any characters. That's just a representation, or it's a lookup table. You have this ASCII table, which has all the combinations in it, starting from 0 to 255. And the human brain calls it just the character. It's not a character, it's just a byte value. So if you try to add something, then what MATLAB literally does is it takes that and adds A to them. Since this is basically a vector, because there are two values there, there's this character A and the comma, it is just one byte and another byte, and we add 2 to the value. That's it. So I can see that probably A stands for 97 and colon stands for 58. So how can I find this out? Well, using the ASCII table. Let's get the ASCII table here. Now you can see that it starts from 0 up to 127 because then there are also the extended values here. The first half is basically the standard table. And here for the character, we have a lot of stuff here, but you can see that lowercase a stands for 97, which I've concluded here. And there's also a column, which is 58. If you look up 58 here, you can see it's a column. So that's basically it. So it's not any character, it's just numbers, byte values. And let me also show you how to define vectors, because this makes more sense then. We use square brackets in, for example, C. What we do is this. We use square brackets to define basically how many elements there are, the length of the array. But here in MATLAB, we have only the square brackets here. And if we do something like this here, we can comma separate them, we can space separate them. So let's do that, 58. So this is basically an array. You don't have to give it a size. You don't have to provide anything. You can just define using square brackets and then fill in the data. So it is basically the same. Now, this code should not work in C because you cannot add a vector and a value because they don't have the same size. But MATLAB has this already sorted out. It has kind of the strategy that if we have a vector or a matrix on one side and a scalar value on the other side, what MATLAB most of the time does is it treats it like element-wise operation. So what this means is that basically, without using any loop or anything, you can just add vectors and single values. Because if you were using C, what we would have done would look like this. So you have the int I, and then I less than the length, 2 in this case, and I plus plus. And then we also need to get the ith value equated and then add 2 to it or a to it, and that's basically it. Of course, we might call this b, and then this is also b. So we don't really have to use this piece of code here. We can just say this plus a, and that's it. But of course, if the size does not match, as in this case, I have to run it twice. You can see that there's a dimension mismatch because there are 2 elements on one side, 3 elements on the other side. How should we add them together if they don't match in size? So that's basically it. But you can use scalars, even though there's a size mismatch. You can add 1 to a vector, and it will add 1 to the vector. By the way, I'm using CLC or clear. Let me explain what they are. If you use clear, remember the workspace that was on the MATLAB interface? That gets wiped out. So it deletes everything that is already defined. So if I say clear, then I don't have any A or B defined because I'm getting rid of them. Now, if I use CLC, it is basically already demonstrated, but it clears the console. So that's basically the way of cleaning the terminal here or the console. This is basically CLS in most of the Unix systems and Windows, as far as I remember. Now, yeah. So we've seen that we can define vectors. We have the character vector here. I said that this is basically the same. If I use, I can also do this, by the way. It's basically the same. Let me show you. So basically using single quotes is extended to the vectors, and you have a vector of single quotes, and there's no such thing as a character. That's only a byte. So it's an unsigned integer, basically. of just 1 byte, 8 bits. That's it. So yeah, is it not possible to combine, for example, what I've tried to do here? Let's say temp, let's say a is equal to 2. How can I combine this? The result should look like this. So what should I do? Well, since I know how to define a vector, what I can do is I can just provide a in here. But that would also not work. And let me show you what the output here is. Temp. And you can see that, yeah, there is no 2 in it. And there's a funny looking face as far as I can see. So why is that? The reason there is that you're using the ASCII table and you're looking for the second character. So this is basically an index at this point. It looks for the second character on the ASCII table. Whatever that is printed out. So this is not the proper way. What is the proper way? You have to use a conversion function. And MATLAB has one of such, which is num to str. So it converts numerical data into string data. And surprisingly, the output is a single quote, even though it's called str. And this is a naming convention coming from C. We use str there a lot, strlen, for example. And therefore, this is called str, even though it's not a string, it's a character. So if I use num to str, what I can do is I can combine these into just one character array, and it looks like this. There we go. So the proper way is this. Of course, you don't have to really do this. You can just do like this, and it gives this output. So then you can go ahead and use this temp to output this info. A is equal to 2. So what about string? Now, if you use single quote, it's a character array. What about string? Let's define a string, maybe the same one here. So what would happen if I add a to it? What now? Any ideas? So we've added a numerical value to a character array. It didn't work, but it converted into bytes and added the values. What about string? If I use double quotes, what's the difference here? So let's see. Interestingly, it works. Now, why is that? Well, in C, we use characters. In C++, std string is introduced. And in std string, you can, if you know some object-oriented programming, you can see that or recognize that the std string is a class, a new data type. And it has a plus operation on lots of different classes, one of them being numerical values, for example. And since you're dealing with strings, when you add string and some other stuff, what you probably want to do is you want to convert everything into string and combine it. So therefore, if you use double quotes and accidentally add some numerical value to it, it will append it to the string, and that's it. So therefore, if you want to be safe, I'd advise you to use string, because most of the time it will do the right thing. But if you use character arrays, that might be a pitfall for you. So now, yeah, you can also add two strings together, but this is called concatenation. So it will just append the strings and create a bigger string. So yeah, that's it. Now, of course, you can use fprintf. As I've talked earlier, you can write to a file using fid, comma, something, and there are formatting strings. You can just %f, %d, etc. It's not a big deal. So about vectors again, we have a definition. We use square brackets, and we can define vectors. Now, most of the time you will see that I'll use commas instead of spaces. Because you have the option, you can do that. But the reason for that is a good programming practice. If I want to separate values in a vector, then I should maybe use commas. If I don't, I might just end up in a different result here. It's just a good programming practice. If the space is gone, then I have a different array than expected. So therefore, if you're careful enough, you can use spaces, but if you're like me, you might opt for commas. So the commas have here a special meaning because we have also semicolons. So A and B are vectors and they are not the same. So it's a row vector, it's a column vector, basically, which brings me to the next point that this is not a vector, this is a matrix. So if it's a row vector and column vector, it's basically a matrix. This is a 1×3 and this is a 3×1 matrix. And I can see that by using a special function that calculates the size of the matrix. I can use size. And let's see what the size is. You can see that the size of A is 1×3, 1 row, 3 columns. And B is basically 3 rows and 1 column. So if you want to, for example, get the number of rows, what you can do is you can just use (1) because this is the first dimension. And therefore, you will get the number of rows here, 1 and 3. You can also give 2 for number of columns. There we go. Or you can get both. And in MATLAB, it is interesting that since you can combine, for example, A and B using this here, this means that I have 2 values in a vector or in an array. I can do the same here, for example, M and N, and use size like this. So if size returns multiple values, then what you can do is you can define the left-hand side in terms of multiple values in a vector and use this. So this is not a behavior that we're familiar with if you're using, for example, C, because C can return only 1 value. But in MATLAB, you can return multiple values. And therefore, you can catch multiple values from functions. And this is the notation. The brackets stand for vectors or arrays, and each element corresponds to each value that is returned. So let's run this. So we have M. Let me run it again. So we have M. Didn't I call it M? There we go. I have M and I have N. So I can extract multiple values from one function return here. So you can see that we are using semicolons and commas, and I've talked about that they have meaning. So what comma does is it's basically places them next to each other. But what the semicolon does, it stacks them on top of each other. So therefore, if you see a comma, then you can safely assume that it will be next to each other. And if you have a semicolon, it should be on top of each other. So, so basically one of them is vertically spacing and the other one is horizontally spacing. So can I combine these? For example, if I have this here, can I come up with a matrix that looks like the following? So let's have 1 and 2 and 3 and 4. Why did I place them like this? I might also go ahead and do this. So there we go. Now what this code does is it defines a row vector A and a row vector B. And in line 4, we combine them so that the first line is A, the second line is B. There we go. Now we've defined a matrix, a vector of vectors. So what I can do is I can go ahead and copy the values here. And get this matrix. What I can also do is I can also use a different way of stacking values. I could also, for example, combine the columns instead of the rows, because the first one did combine the rows. So we might also go ahead and say that 1 and 3, and the second column should be 2 and 4, and then stack them together such that we have the following output. I'm not saving, I guess. There we go. Now there are two ways of approaching this, as you can see, line 1 and line 3. Now in MATLAB, we don't really have to define the matrices as vectors of vectors. We can skip these parentheses here, this one, and also this one. Is basically not necessary. You can just give one bracket. And what it does is 1 and 2 should be the first line, they should be side to side, and then 3 and 4 should be, again, next to each other. And we should stack them so that we have two basically rows. So I can use this shorthand and define a matrix. Now, what will happen if I do it like this in line 4? I got rid of the extra brackets. I have 1, 3, 2, 4. So what do you expect here? So what should be the result here?
Error.
Why? Why should this not work?
Not seem good.
Well, if you think about the semicolon and comma again, this should look like this. So first we have 1, and then we go down one line, and then we have 3, and then we should put a 2 next to it, and then go again 1 line down and place a 4. So if you read it, this should be basically what you think of, because here it's the same. I place 1, and then next to it there's a 2. I go 1 line down, and I have 3 and 4. So that's it. The first one works because the size matches, but each row here has a different size. So it's not able to combine them and create a new matrix or vector out of it. So therefore, you cannot do this. You have to use this here. Or you can add some values to it. For example, like this. Then the size should match, therefore we should be able to combine. There we go. So, of course, we don't create matrices like this all the time. We might use some predefined functions. For example, if I want to have a 2 by 2 matrix, I can use zeros. It will generate a matrix consisting of zeros, and the size is basically row, column. There's also ones, which we use a lot, which is basically the same, but it has 1 in it. You can also do zeros plus 1, if you think about it. There we go. So ones is really not that necessary. We have the identity matrix, which is spelled weird in MATLAB, which I don't get really. Instead of having identity, we have to type in I. I don't know the reason for that, but there it is. So you can use determinant on that. By the way, let me also tell you that the default variable in MATLAB is called ANS, which stands for the answer. So if you are interested in the last result that is printed out or defined, then you might use ANS in order to use that. If you forgot, for example, to say that x should be equal to I. instead of X. If you don't define it, it will become ANS. So that's it. So now, of course, we've seen matrices briefly. We've seen vectors. Now, what would happen if I, for example, try something like this? By the way, you can use true, false, or logical 1, logical 0. So what do you expect from this now? Let's say temp. For some reason, I want to combine the value 1, the character array AST, and the value true. So am I able to do this, or will this work? Now, again, in C, we use a certain data type for a vector. This means that we are using a block of memory that consists of elements with the same size, and the data type should also be the same. So it uses identical elements to combine and generate a vector. Therefore, we don't have the ability to try to combine different data types. If you want to use such a thing, then you have to use curly brackets, because it is a totally different data type. Let me show you. It's basically a cell array. Now, we don't use this that often, but you can combine different data types into just one data by using curly brackets, which is called cell. By the way, in MATLAB, if you don't know certain, for example, codes or functions, if you don't remember what it really does, then you can remind yourself by using help and then the thing that you're searching for. Now, this gives us a brief introduction to its usage or its meaning. If you want more, then you can use doc, which is the shorthand for documentation, and then you can look for the actual documentation, which gives much more in-depth view of what you're searching for. Now, and let me also remind you that most of your Google searches will end up in this documentation page, which is also available online. So you might just ask MATLAB directly instead of Google. So, yeah, we have talked about cell, which is not really that relevant, but we have a different thing, which is much more usable, which is called struct. But contrary to the C version, here, struct is a function, basically, which generates a struct. We don't really use it in the sense of object-oriented definition, but we use a function called struct, which generates our struct automatically. For example, we can do the following. Let's have a name, and let's have, for example, age, and then let's say married, and then let's say false. For example, I can create the struct here, which is basically a C-type struct. Let's run this. And if I enter temp, you can see that it is a struct with fields, and it has fields name, age, and married, and then we have different data types. So this makes more sense if you are trying to combine different data types together. For example, you have a simulation and you have a report to generate, and then each simulation should basically return you a structure about the simulation data. So struct might be useful for you, so it's good to know. And it's fairly easy. You just give field names. It's a key value pair, basically. Yeah, that, I guess, concludes our variable and arrays discussion here. Of course, I know that most of you are familiar with the if statement here. So let me just talk just briefly on it. So here I have written a code that basically has if in it, but also doesn't have if in it. So Basically, I have used if, but I've also not used if. So that's an interesting code here. The reason for that is the if statement on its own looks for the statement, and it only works if it's true. And if you directly give it true, then it has basically no meaning. Deleting the line 2 and 4 or commenting it out doesn't have any effect on it. So let me show you. So A is 2, B is 2. So let me introduce if again. You can see it works the same. So can it be useful? Most of the time it can be. And the reason therefore is that, for example, I might want to use A equals 3 and A equals 4 for some reason. And I want to have A squared, for example, here. So if I have two different pieces of code and I'm trying to come up with the actual code that is useful, what I can do is I can use this if statement here. I can switch basically to false to try the other methods and look at the results. So you don't really have to copy your scripts and all the code that you've written. You might have little if options here, true, false, that tries different methods, for example. So it's basically the if not def pre-processing command, if you know what I mean. So yeah, if on its own is not really that interesting. So you can have else if and then true. Basically, now I have written a code that has no else in it because true or false, and that's it. But yeah, if on its own is not really that interesting, as I've tried to make my point here. So let's define therefore I equals 2, for example, and then increase the value of I if I is less than, for example, 6. So there we go. Now you can see that the condition here is checked. If 2 is less than 6, which is the case, I would be increased and I should be equal to 3. Now, of course, this again has not that much meaning at this point. I is equal to 3 and that's it. But what happens if I go ahead and copy and paste it a bunch of times? Now, at some point, this if block lost its meaning. But up to that point, it was used. So what I mean by that is I started equal to 2. This is executed, it becomes 3. This is executed 4. This is executed 5. This is not executed. This is executed 6, and at this point, 6 is not less than 6. Therefore, from this point on, if has lost its execution basically, because I is not less than 6. So you can basically already tell what I'm trying to achieve here. This is basically the definition of while. And if you're using assembly, then you would basically execute if, so comparison, and then you get a result, and then you jump again to the if until the condition is violated. So therefore, instead of copying and pasting these ifs here, what I can do is I can just get rid of all of them and replace it with while. So this is basically executing if over and over again until the condition here is violated. So therefore, I is equal to 6. Now, as you can see, there are 3 steps and I'm just counting. I is equal to 2, a variable definition. The condition in line 2, I is less than 6, and then increment of I in line 3. So if I'm doing nested loops, if I'm, for example, copying this and then pasting it in here, change the variable to j, and then if I'm going on with this, it becomes a real pain because I've written so much line of code to count nested. So that's not ideal. Therefore, we have something else. And that's, of course, the for loop. But the for loop is a bit interesting because in for, what you do is you do this. And you can basically use for in two different ways. One of them being the following. You have I equals and then an array or vector of values. For example, you want to start with 2, 3, 4, 5, and you don't want to have 6. This is basically the equivalent here. And you can basically use this instead of this. The increment here is in the values. The starting point is here, and the stopping point, which violates less than 6, is in here. So this is a combined and compact way of writing while loops. This is one way of doing it. There we go. Let me run it again. 5, and if you want to have 6, then you should also include 6. Therefore, that's it. So this is not for in the usual sense. This is basically for each. If you're familiar with that, in other programming languages, there's something called for each, which basically uses a list of values and a iterator, and then you just iterate through all the lists here. So that's available in MATLAB. But you can also create this list by using a different operator, which is the column operator. Now, this is basically a way of creating a vector, an incremental valued vector. So it starts with 2, it ends at 6, and the increment value here is 1 by default. So you might also create a vector using this. So this is 1 to 5, for example. If you do this, you get 1, 3, 1, 2, 3, 4, 5. And you can also specify an increment value here. For example, 0.4. And then what we can do is we can use disk and we count like the following. So this is basically if, for, and while, which we will use most of the time. And there are also functions, and defining functions in MATLAB is pretty straightforward. Before you create the function itself, you should create or write down the definition of it. Before you implement it, write the definition. Why am I telling you this? Because let's say we want to use a function called add. So I want to provide 2 values to it, and the result that should be returned to me should be C. So if I imagine that I have the function already, this would be the usage of it. So I will copy this usage, create a new file. By the way, I'm going to call it add, because most of the time, if we define functions, the name and the script, the name of the function and the script name should be the same. So there we go. I've defined my function. So this was the usage. I'm going to pass in 2 variables, and the function is named add, and it will return the value, and I will store it in C. I did the same here, and now I have to implement it. Now, if you, again, compare it to C, in C you should use return. But here you define it like this, and if you set the value of C to, for example, x plus y, then you don't use any return. So let's define 2 and 3. There we go. We have implemented a function. Now it is also possible, and I've also exemplified it, it is also possible to return multiple values. The only thing that you should do is you should just set the values, and that's it. For example, my add function for some reason also returns the difference between them. I can do that. What I have to do is I have to copy this definition here, which is also the usage here. And that's it. So you can see I've returned multiple values. There's no return, as I've told you. There's just this definition, the way of defining this, and then you have to set the values, and that's it. So whatever the last value of this is, that will be returned. For example, if I use the same variable over and over again, the only thing that matters here is that the last value is going to be returned. So you can see that C is equal to 2, even though 2 plus 3 is not equal to 2, because I've set it to 2, and that was the last operation of C. So now I guess I have talked enough about MATLAB and basic MATLAB usage. So let us give it a little break. And after the break, I will be talking about the symbolic toolbox and the control system toolbox, and then we will be done for today. So let's have a 5-minute break. And okay, let's continue with the symbolic toolbox. Now, we've talked about basic MATLAB, and I just briefly mentioned some aspects. In this course, most of the time, it's not really about the basic MATLAB usage. That's already a prerequisite, but it's more about the symbolic toolbox, because what we want to achieve here is that we have some theoretical knowledge. Let's say, for example, we know how to compute the roots of a polynomial. Let's put that on the table. Now, if we know that, we want to basically use MATLAB that in a way simulates the steps that we know to the theoretical knowledge. So if we have, for example, an algorithm, we want to implement it here and see what it really gives us in terms of, for example, outputs. Since we are dealing here with controller design and control system design, we have to have this first bit of synthesis here. So therefore, we need to have a way of dealing with unknowns. So I have told you, for example, if I want to define a certain variable, I have to provide the value before I start. But what if I don't know the value of this variable? What if I want to compute it? So then I cannot use MATLAB or basic MATLAB. I have to use a certain helper here. So you might have heard about, for example, Mathematica, which is a symbolic language, basically. It's possible to use, for example, a certain symbolic language like Mathematica, but MATLAB has also a neat toolbox, the symbolic toolbox here, that helps us out here. So what I really want to do, for example, is I want to solve this equation. Let's have 4 times x and then plus 4 equals 0, for example. I don't know what x is. I want to solve x. Therefore, I need to somehow define x as a variable, as an unknown, and then I should manipulate it and get to the result. So therefore, what we can do is we can use this sim here and say that we will have a symbol, an unknown, that has no value to it. That's just x. And then I can manipulate this. I can, for example, say, let's, by the way, you can see that we have to store it in some variable here. So interestingly, if I type in x, it will give me an error or an undefined variable here, unrecognized variable here. The reason there is that there's no x. So this is basically returning me something. So let me explain you what really lies in here. These days we are familiar with, for example, the rendering engines and the game engines here. This is basically a symbolic engine. So we are communicating with a program that's already running, for example. And I have to tell the engine that I have a certain object, and that's it. And I will manipulate this object, and it will give me responses. So I'm continuously trying to communicate with the engine, symbolic engine here. So therefore, by using the sim function and giving it a name here, x, it will just generate an object, but I don't have access to it. So it returns me the axis, but I have to store it in a value or in a variable here. So the definition becomes a bit confusing here, because here's an x and there's also an x, and then I have also this here. So yeah, I will solve this in a minute, but this is the most basic code here. You can see that there's a trivial output here, which says x equals x, but let me remind you that this x is a symbolic x, and this one here is a MATLAB variable. So in order to overcome this confusion here, what we can do is, instead of calling line 1, we can say that we have some symbols and we want to store them in these variables here. So the definition and the variable is the same here. Instead of using this for shorthand, what we can do is we can use this. So basically we have x now, and this x is just an unknown. Now the symbolic engine here knows how to take the square of such an unknown to combine x squared and 4x and 4 together to build an expression. So it deals with all those details. Of course, you can use pen and paper and just write it down. You can just have an x and then square it and add 4x and 4 together. But the symbolic engine has more capabilities to it. For example, I can solve this equation. And therefore, the symbolic toolbox has a function called solve. And if you provided the expression, it will try to solve it. There we go. It gives me the roots of this polynomial. And you can also see that I didn't write down expression equals 0, but I can do it. And if I omit this equals 0, then it will automatically assume that it should be equal to 0. So basically, using sims x, y, z, k, whatever you like, or whatever you need, you can define symbolic variables, and you can use those variables in order to build some expressions. And you can use those expressions. For example, you can solve for its roots, or if you need, for example, to get the coefficients here, you can use coefs function and then give the expression, and it will give you automatically the coefficients here. Now, interestingly, first of all, as a control engineer, you might expect that it should give us 4, 1, 4, 4. The order is inversed for some reason. Now, that's one thing. And another thing is that, again, as a control engineer, you might not expect to have 4, 1 as a result here, because the coefficients of a polynomial, if I think about it, is 1, 0, 4 in this case, because I automatically adjust to that. If there's a missing term, it should be 0, and it should be ordered so that the first coefficient is the highest order component. But that's not the case here. Do you have any idea why this is not like it should be in our minds? So why is this different? And why is the result 4, 1, despite the ordering? Why don't we get a 0 somewhere there? And more interestingly, I can show you that, for example, plus k, let me change x to s, maybe that makes more sense here. Now, s squared plus k plus 4, that could be a polynomial that we're looking for. But the result in terms of coefficients is 4, 1, 1, which is even more confusing now. Because I guess, at least if you think about it, it should be, or I feel like it should be 1, 0, 4 plus k. Because it's s, the Laplace term. So it should be the powers of that, or the coefficients of that. But that's not the case here. And the reason is that the symbolic engine uses a tree structure for the expression that you give it. For example, you have s squared, 4, and k. Those are the components of the expression. And if you tell the symbolic engine to return some coefficients, it will look up these three components. This has coefficient 1, this has 4, and this has 1. Because K and S are unknowns and they are equally unknown to the symbolic engine. They don't have any special meaning, like the Laplace S or something else. So therefore, it treats them equally. What you have to do is you have to provide a variable that you're interested in. For example, S. I want the coefficients of S. In that case, it will return something different or something more expected, I guess. K plus 4 and then 1. Of course, the ordering is still not right, and we are missing the missing term, basically the zeros here. So the symbolic engine looks for the S terms. It has S squared, the coefficient is 1, and then there's 4 plus K. You have to tell implicitly that you want all the coefficients, all the possible outcomes here. So it looks for the highest order, which is 2. It means that it should return 3 coefficients. It fills them out, and if there's something missing, it is equal to 0. So this behavior now suits us the most. You can see 1, 0, K plus 4. If I give you this vector, you would automatically write S squared plus K plus 4. Otherwise, if you look at the vector 1K plus 4, for example, then you might also write down S plus K plus 4. So it doesn't make really sense. So we can safely assume that the coefficient vector here has basically all the information we need to reconstruct the polynomial. So let's say we have, for some reason, the coefficients written down. And it could be a feedback K. So the controller is K, and then we have some polynomial. We want to see what the change is here in terms of the roots of the polynomial versus the change of K. So I want to change K, and I want to observe what happens to the roots, basically root locus. So how can I achieve this using the symbolic toolbox? Because we know that we can define a transfer function, use the rlocus command, and we're done. But that's not it. We don't really want to use the root locus if we are trying to get the theoretical knowledge here, if you want to analyze it, examine it. So I want to be able to do this on my own. That's what I'm trying to tell you here. So how can I achieve that? Well, basically, I should plug in some value into my expression for K, and then I should get the coefficients of that polynomial in terms of S. And then I need to look at the roots of those coefficients. So this is basically a 3-step thing here. So if I want to substitute a value into K, I can use subs command. Now, the subs command needs the expression itself, needs the variable that I'm taking into consideration, in this case K, and then it needs a value. For example, let's plug in 1. So this subs command will generate S squared plus 5. Now you can use a for loop and then increase the values of K. You would have what you want. The only thing left here is that I need to solve here. For example, I can use solve here. This should be equal to 0. And there we have our roots. So if I change K, it will automatically determine the actual roots, the corresponding roots here. Square root of 6, negative, and plus. So symbolic engine gives us this feature here where we can substitute, get the coefficients, and there are much more commands that we will use, of course. For example, what we can do is we can do the following. We can have a system defined. By the way, I say this is a system, but it's not really a system. It's just an expression. And it can look like this. Now we have GS. Now in the control system toolbox, you can also define a transfer function, but this is not a transfer function. This is just a representation. This is a simple fraction here. So if I, again, use K and look at the following here, for example. Now, this represents a closed loop, a p-type controller closed loop. We have a plant, a controller, and then there's the closed loop. Now, of course, this does not look very usable or readable, at least. So what we can do is we can use simplify here. And the simplify function is pretty much self-explanatory. It simplifies the fraction, that is. So we have k divided by k plus s plus 1. There we go. If we don't use simplify, we have this explosion of terms here. But if you simplify, it simplifies it. I can also extract the numerator and denominator here. Therefore, we have a function called num then. Numerator, denominator. Of course, we've seen also an example here. The numerator is one part and the denominator is another part. So it returns me two parts. Therefore, I have to use line 5 in order to decompose it into its numerator and denominator. So it returns multiple values in this case. So now you can see the numerator is k, the denominator is k plus s plus 1. And then I can, of course, use subs into the denominator. And for k, I can give some value. And then maybe you solve, or I can also use the coefs here. Of course, I should say I want all the s coefficients here. We messed up this part here. There we go. Now it gives 1 and 2 because we've plugged in k equals 1. So, and then I can use roots on this. Maybe the roots of the coefficients. And then we have basically -2. So if I increase k, I will get different values here. Therefore, I might go ahead and do the following. Since I'm substituting here, what I can do is I can say, let k start from 1 to 10, and then generate the coefficients and look for the roots here. Basically, this is root locus at this point. Of course, we have to substitute. Okay, now you can see one of the issues that I wanted to talk about. Now, I have a piece of code, but for some reason, it does not work as expected here, and it gives me -k -1. The reason behind this is the following. We have a symbolic variable k, and then we have also a placeholder, which should be the value of k. So there's symbolic k and then the numerical value of k. So if I don't distinguish them, then I may end up in this case, because I've overwritten k here. I've lost access to k. So we should avoid to do this. Therefore, we would use, we have to use placeholders. For example, instead of using k, because this is a symbol that I'm using here, I might use kval, the value of k, or kv, or k something. So in this case, kval seems okay because I want to use the subs here. And in subs, I need the expression, the old symbol, and then the new value for that symbol. So if I don't want to lose k here, I have to use kval. Of course, there is a way where we can use k here, but it would confuse you. So therefore, I'm skipping it. It is possible to use k instead of this symbol k here, but we should rather not. So instead of using the variable itself, it's already occupied, we should go ahead and use a placeholder for it. So in this case, let's run it again. Now you can see that there's numerical data. You can see that it outputs what we want. So instead of, again, using this notation here, what I like to do is I'd like to define a k vector, because that will hold all the values that I'm going to try. And then I want to store the results in another vector. and maybe then try to plot them. So instead of using this here, we can define this as a vector, kvec, and for each value in this kvec, I can go ahead and calculate this. Now, of course, this is one method, and this would work, as you can see, but I cannot store the values here. I want to store the roots of this polynomial for that individual k value. So let's say poles, for example. Now, you can see that I want to define a vector. I know the length, but I don't know at which index I am. Do you see the problem here? I want to define poles. I want to store each value from this into poles, but it's not really possible in this case. It is possible when I use an empty array or vector. So for defining a vector, you don't really need to put anything in it. You can just use the square brackets and that's it. So I can do that. But how can I store this result here in line 10 into poles? So any ideas? I want to store these values because I need to, again, then once I'm done, I'm going to plot this k versus the poles here. So how can I do this? It's possible to use multiple stuff here, but the best way would be to say poles should be expanded one element at a time. So this is one way of solving this. You can see that poles for the first element of kvec is empty. So what it translates to is the following. I'm trying to combine an empty poles with roots of this clef. And if it's, for example, what is the first value here? I guess -2. So this becomes basically the vector -2. And in the next iteration, I have already -2 here. And the next root is, for example, -3. This will be extended to -2, -3. In terms of memory usage and performance, this is not ideal, but this is flexible. So you don't really need any length information, anything at all. You're just combining. You're copying, but that's not really a big deal here. A better way, let me first show that this works. So there's a better way. If you write in poles, you can see we have all the poles stored in this variable. Now, a better way would be to use a vector to predefine it, because we know the size of it, because it depends on the size of kvec. If I have 10 elements in it, then I will basically, depending on the order of the transfer function, etc., etc. But in this case, I know that this will return me just one root. Therefore, I know that there are only 10 elements here. So this for will be looping 10 times, and that's it. So therefore, I might go ahead and use the zeros function. And I can hard code it because I know that it should be 1 row and 10 columns. That's one way. But again, this is not that flexible because I have hard coded it. So maybe I can acquire the size from kvec. And I know that kvec and poles should share the size. They should be the same size. So instead of doing this again, I'm going to copy the size of kvec, and I'm generating a zeros vector out of it. So line 7 is a pretty neat one because you can use it over and over again. If you know that you have a certain structure somewhere and you want to copy exactly the same structure with 0 in it, then you can use line 7. Of course, if I use such a thing, and I know that I have a certain index, instead of using this for each approach here, I can use the usual approach where I is equal to 1. So I'm looping element by element, by the way. And I can use length, which is another function that determines the length of, for example, kvec. So you can see that I need to use kvec I here. you might substitute this, or you might call this kval equals kvec I. And then you use that kval in order to substitute it into the expression and then get the coefficients, and then the roots of the coefficients are determined here. Now, instead of expanding the vector over and over again, I can go ahead and say that the ith element of the poles is basically the roots of this coefficient here, coefficient vector here. So let's run it first. Now, this is a better code in terms of performance and memory usage, because you're pre-allocating your vectors and the for loop doesn't extend the vector whatsoever. So basically, it is efficient in terms of memory usage. Of course, it's also efficient in terms of expanding it, because if I increase kvec, all I have to do is increase it. I didn't hard code anything else. So line 7 will calculate the size of the vector kvec, and it will adapt to it, and the for loop will also adapt to it. So therefore, we have the poles up to 101. So once we have those poles, we can also go ahead and do something interesting with it. What we can do is we can basically try to plot it. Therefore, let me show you the plotting code here. We had a little disconnection here. Now we're back again, I guess, and we're recording. Okay. Now, we create figures using the figure command, and you will provide a certain value to it, which will be basically the figure number here. What I like to do is I like to use CLF, which stands for clear figure. The reason for that is that I'm using also hold on, and this hold on here basically stacks up the plots that will be plotted onwards here, and maybe also grid on to have a nice grid that helps us in reading values. So line 14 will be basically coming up occasionally. So at this point, we will then use the plot function. And if you want to know the details of the plot function or figure, you can just use docplot figure. You have to give the x values, a vector of the x values, and the vector of the y values, and you're good to go. It will plot a 2D plot. There are also line specifications, which I'm briefly going to touch on. But there's a detailed documentation. You can try this out or look into it. It's pretty fun to toy around with these stuff. But I will just briefly use it in this case. Now, the roots of this polynomial are stored in poles. And basically, I have just a vector here with values. Since I've used a basic system here, 1 divided by s plus 1, I can see that all the values are real. But that might not be the case for this, for example, here. Let's have this. Now, if I change this, I can see I have changed the order. Therefore, I should also update my poles here. Now, before I plot it, let me show you. Now you can see there's a type mismatch, or basically a size mismatch, because we have a second order transfer function here, and the closed loop would be a second order transfer function since we are using a p-type controller. But the poles are allocated such that the size is calculated by the vector size of kvec. Therefore, I have to adapt this here. I know what the order is. So let's have 2 rows and as many columns as kvec. So then this kind of changes here. So what we can do is we can just say, for example, this. We didn't talk about indexes, but if you use this here, or if you give it a vector, you're basically picking those rows. The first row and the second row will be picked here. Or you can just skip this and provide a column, which stands for all the possible dimensions. Yeah, basically what I'm trying to do is I'm trying to calculate the roots, since this would be a 2 by 1 or 1 by 2, we will see. Vector, I'm storing it accordingly. So let's try it out first. Takes quite some time. Now we have the poles. Now you can see the size of poles, which we've already defined, is 2 by 100. So we have 2 rows. Each row corresponds to each pole of the closed loop, and then there are 100 points because we have 100 K values. So the interesting thing here is that we have complex values, and we can determine the real parts and the imaginary parts of those, and we can also plot them. So basically, if you know the S domain, we have the x-axis as the real axis and then the y-axis as the imaginary axis. So since I have to provide the x-axis and y-axis, what I can do is I can use real and then poles here, which will calculate the real part of the poles. And I can also give the imaginary part here, which will calculate the imaginary parts. So that's basically it. If we run this, I should maybe decrease the thing here, the upper bound on K. And it shows us an interesting plot. The reason behind this is that we've used plots directly. So we're not connecting them. We have to place individual points. And you can do this by giving some extra arguments. For example, I provide an X, so it will try to place X's on those coordinates, which are calculated by the real and imaginary parts of the poles here. So let's try that out. So you can see now that one pole is going to infinity and the other one is going to minus infinity at point 0.5. So this doesn't look like a S-domain plot, but it's basically an S-domain plot. The aesthetics don't match here. The only problem is that, but you can see that I can see by increasing K from 1 to 20, they will travel along a line here. To have a better example, we might go ahead and try to change it. Let's have S plus 2 times S plus 1, for example. So in this case, the plot should change a little bit. Real imaginary poles. So let's see. Oh yeah, of course. Let's plot each pole individually, or even just the first one. Yeah. Basically, this is a root locus plot, but it's not really easy to see if it's really in the S domain. Therefore, let's go ahead and copy this and give them different colors to see that one branch is one and the other one is basically the other one. So I'm specifying here some symbols that are predefined. You can look them up in the documentation of plot, but you can see that R stands for red, B for blue, and X is basically the marker. If we run this, you can see that one branch of the root locus plot is red, the other one is basically blue. And you can see that the origin here is on the right somewhere, and they are basically approaching each other, and one is going there and the other one is going basically down. So you might ask to yourself, what is the point of having the root locus plots calculated using the symbolic toolbox? Well, this is basically an example. Of course, we don't need to really calculate the root locus plots if there's a function for it, but we know that we can use basically the formula for the closed loop. We know that we have a certain parameter in it, and if we vary that parameter, we can see how the poles are moving. Now, in this case, it makes sense to try to implement an algorithm that can calculate the root locus, and that this is a demonstration of that, for example. So let's have one at the origin, for example. What I have to do is I have to just change this. I can also make this adaptable, but for now I will skip that. Give it a new color. You can see it looks more like a root locus plot at this point, but as I've told you, this is not for root locus. This is not meant for root locus, of course. But if we have a theoretical point and if we want to try and test the limits, then we can use the symbolic toolbox here to try to emulate all the steps that are necessary here. So I can talk about this on and on, but basically we have covered the topics that I wanted to cover. Now, in the PDF that I'm going to upload as soon as possible, you can see there are some code pieces that you might want to look at and to try to remember. We have covered the display function, we've covered if, there's while and for, and some explanations about the functions, the usage of them to combine characters. And then there's the symbolic toolbox part, which was the second part of today's lesson. You can see there are different definitions, but the second one here is the most understandable and suitable for us. So I highly recommend to use the second line here. And then there are some functions that I have tried to briefly introduce you to. There are coefficients, coefs. This one is not really that used, but you can see that we have to use coefs in a special way. And we have some helper functions, and there's a list, expand, collect, combine, factor, etc. So you can look up the symbolic toolbox page from MATLAB. And there's a bunch of code there. You can see we've already covered them. Now, from the control system toolbox, most of the time we will define TF, ZPK, we will use them. And there's, for an example here, this is also a transfer function. And this one here is also a transfer function. Now, we have two ways for defining a transfer function in this course. Don't mix them up. If we are trying to design a controller, if we are trying to try something on the transfer function or the plant, then we will start with the symbolic toolbox. But at some point, we have to define the same transfer function in the control system toolbox to be able to call, for example, the function step, feedback, step info, etc. So it's the symbolic toolbox and the control system toolbox are not compatible. You cannot give it in a symbolic expression and expect it to work. What I mean by that is, let's skip all this part and let's focus on GS. Now, if I have such a GS, I cannot call step on it. So that's important to note. And the reason behind that is that step is a function in the control system toolbox, and GSS is not even a transfer function, it's just an expression. It is a fraction here and nothing else. So you can see that the class of GSS, for example, is sim, and it's just an expression. Step does not know how to handle this. But on the other side, if you have TF, for example, you are defining a transfer function, and it also reminds you that this is a continuous time transfer function. So it's important to note that we have multiple ways of defining transfer functions, but we should be careful if we are using, for example, some functions from the control system toolbox, then the transfer function should be a transfer function object. We should convert it into TF. But if we are, for example, trying to use some symbolic calculations on it, then it will be a symbolic expression. At some point, we need to convert them, and that's basically important. Now, at this point, I will skip these parts because they are just basic examples, and then we have a code where I show how to basically plot stuff. There are some extra stuff, but you will see that in the upcoming lessons. So yeah, I would say that this is it for this week, but next week and the weeks from then on, we will have some control system knowledge in it. So this was basically just an introductory level. So basically keep that in mind. And if you have issues